Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we are here to put science in your brain.
This week is the Lunar and Planetary Science Conference. Normally, this meeting would bring together several thousand planetary scientists at a conference venue in Texas. And I really wanted to be there. But because of COVID times, this meeting is instead being held like everything else online. And we here at the Daily Space are going to do the best we can to pour through the mix of live and pre-recorded science to bring you all of the planetary news we can. But before we do that, we're going to bring you the news from the rest of the universe.
And our first story takes us out to the edge of the observable universe, where a rare and brief event was spotted not once, but 3 times. The event, fast radio bursts, millisecond-long spikes in radio waves from distant objects, quite possibly dead stars with powerful magnetic fields called magnetars. Because fast radio bursts are so very brief, you have to be looking in exactly the right direction at exactly the right time with just the right equipment to be able to see them. And until now, just not that many have been spotted. But astronomers using the 500-meter FAST telescope in China are working to change that and are conducting a survey to systematically look for fast radio bursts and determine their locations and how common they actually are. In a new paper in the Astrophysical Journal, with first author Shen-Hu Niai, the team publishes 3 new fast radio bursts located 4 to 5.5 billion light years away. Based on how large an area they observed and how long they observed, this team estimates that if we could observe the entire sky with the right instruments, we'd detect 120,000 fast radio bursts every day.
This survey is our latest recipient of the Babies Award for Bad Acronyms and Backronyms in Everyday Science. The survey's name is CRAFTS, which stands for Commensal Radio Astronomy Fast Survey, and has an acronym nested in an acronym and randomly uses the first and last letters of that nested acronym. Well played, acronym creators. Well played.
Well, these kinds of surveys give us insight into the universe as a whole. To understand the universe, sometimes we also need to focus on understanding our own world. Or in the case of this story, the gravity our world and other things exert. In a remarkable new paper in the journal Nature, researchers from the University of Vienna show how they measured the gravitational pull of a 2-millimeter gold sphere weighing just 90 milligrams. This was accomplished by using lasers to carefully measure how the effects of the sphere's gravity changed the swinging of a tiny pendulum of glass just 4 centimeters long and half a millimeter thick that was capped with matching gold balls. The suspended pendulum was on a glass fiber, a few thousandths of a millimeter in diameter. According to co-author Jeremiah Sfaff, we moved the gold sphere back and forth, creating a gravitational field that changes over time. This causes the torsion pendulum to oscillate at the particular excitation frequency. These gold balls are roughly the mass of a ladybug. This experiment shows that it may one day be possible to measure traces of dark matter and dark energy by how they affect the gravitational field. Study lead author Tobias Westphal puts it this way. According to Einstein, the gravitational force is a consequence of the fact that masses bend space-time in which other masses move. So what we are actually measuring here is how a ladybug warps space-time. And let's face it, that's just kind of cool.
The changing gravitational force a pendulum, a person, or a detector is able to register is related to the changing locations of everything around us. This means that when a plane flies overhead at the smallest level, your weight is reduced as you are pulled toward that plane. You won't notice this. Your bathroom scale can't measure this, but the change in the gravitational field is real. From 2009 to 2013, the ESA's GHOST mission carefully measured the Earth's gravitational field. And in a new analysis of the data, researchers have been able to measure the Earth's crust and upper mantle. By better understanding these parts of the Earth, we can gain new insights into how the Earth's plates move and initiate reactions like earthquakes. Using this data, along with seismological observations and data on the properties of the crust, scientists have created a new model that is already helping us understand how the Earth continues to rebound from melted glaciers and the spreading rates of mid-ocean ridges. This work is published by J. Dalia, S. Lebedev, and N.L. Kelly in Geophysical Journal International, and I look forward to seeing how this new model improves our understanding of our changing Earth. After the break, we'll dive into new planetary science describing both alien worlds and planets right here in our solar system. It's been a while since we talked about exoplanets around here. Oh, no, wait, no, it hasn't. We always seem to be talking about exoplanets, and today I have 3 different stories to share. First up, distant planet JG1132b is a sub-Neptune that lost its atmosphere due to being too close to its young hot star and faced with the intense radiation, making this sub-Neptune more Earth-sized. But wait, what's this that the Hubble Space Telescope has detected? An atmosphere? It seems that, in the face of losing its atmosphere, JG1132b found a way to acquire a new one. This secondary atmosphere was analyzed based on a combination of Hubble's observations and some computer modeling. Instead of the primordial hydrogen-helium atmosphere, atmosphere 2.0 is made of hydrogen, hydrogen cyanide, methane, and an aerosol haze. The haze is likely photochemically produced hydrocarbons, similar to the smog that can form here on Earth. Even more interesting, this new atmosphere has possibly been influenced by volcanic processes in the interior and on the surface of JG1132b. And those processes are due to the tidal heating from the gravitational pull of the star and another planet, plus the elliptical orbit, which gives those pulls some needed variation. Lead author Mark Swain sums up the work, soon to be published in the Astronomical Journal. How many terrestrial planets don't begin as terrestrials? Some may start as sub-Neptunes, and they become terrestrials through a mechanism that photoevaporates the primordial atmosphere. This process works early in a planet's life when the star is hotter. Then the star cools down, and the planet's just sitting there. So you've got this mechanism where you can cook off the atmosphere in the first 100 million years, and then things settle down. And if you can regenerate the atmosphere, maybe you can keep it. Chalk up another point in the column for sub-Neptunes being able to shift to super-Earths, I guess. Of course, much of current exoplanet research seems to have the goal of finding another habitable world. As I mentioned in the previous story, it seems that surface volcanism may be influencing the new atmosphere, and it turns out it's not just volcanoes that can have an effect. In a new work published in the Planetary Science Journal, researchers determined that rocks and rock types can influence the composition of the atmosphere, which in turn leads to the habitability of the planet. Lead author Kostov Hakim explains, we want to understand how the chemical reactions between the atmosphere and the surface of planets change the composition of the atmosphere. On Earth, this process, the weathering of silicate rocks assisted by water, helps to maintain a temperate climate over long periods of time. When the concentration of carbon dioxide increases, temperatures also rise because of its greenhouse effect. Higher temperatures lead to more intense rainfall. Silicate weathering rates increase, which in turn reduce the carbon dioxide concentration and subsequently lower the temperature. Once again, this work was done through a lot of computer modeling, testing how various conditions affected the weathering process of rocks and how the results could impact any atmosphere. All of which helps us understand the probability of finding that first truly habitable world. From the atmosphere to the surface to the interior, this last story dives down into the mantles of rocky super-Earths. The work was published in Nature, and it involved lasers. No, Seriously, lasers were involved. Big, powerful lasers at the Lawrence Livermore National Laboratory were used to compress iron oxide to pressures between 3 and 5 times that of the core mantle boundary here on Earth. The compression took nanoseconds. Nanoseconds. A little chemistry now. The iron oxide ended up at twice the density of another common mantle mineral, magnesium oxide, and it underwent a phase transition in the process. Here on Earth, you can easily mix the two minerals together in the mantle, but with that phase transition at high pressures, that's no longer possible, which means that in a super Earth, there could be some new physical properties we don't see here on Earth. Lead author Federica Capari explains, not only are the atoms packed more tightly, this new material phase of iron oxide is associated with a dramatic drop in viscosity, which plays an important role in the convecting motions inside the mantle. The rheology of a large extrasolar planet might be completely different than that of Earth, and it's related to the different material properties at more extreme conditions expected inside exoplanets. This research shows a new way to experimentally derive some information about the characteristics of a type of planet we don't have in our own solar system. And that is incredibly impressive to me. I know I joke a lot about planetary formation theories, but I genuinely love all the work being done. And again, this story involved lasers. Woo! When we return, we'll try to get a handle on the amazing work coming out of the Lunar and Planetary Science Conference. And whew, is it a lot?
And now, let the LPSC fire hose begin. This conference is presentations with all the latest news from around the solar system. This morning, the big show started with a deep dive into the landscape that the Perseverance rover now calls home. While we have a pretty good idea roughly where a spacecraft should land, detailed mission planning can't start until the exact landing spot is known. For just over 20 days, Percy has sat on the red planet, taking in its landscape with amazing cameras. And while mission engineers do a complete check of the rover systems, team scientists have been planning their future journey through Jezero Crater, shown here, and out to the Nilium Planum beyond. Jezero Crater is a much smaller geographical area than Curiosity's Gale Crater. It is also a lot more hazardous and more interesting due to that dangerous and complex geology. Figuring out a path that keeps the mission safe and allows sampling of all the cool rocks is an awesome challenge. And to judge from Twitter, a whole lot of planetary scientists just want to run around wildly picking up rocks. Making things more complicated is a particularly dangerous section of land between the Octavia E. Butler landing site and where the rover most wants to go. Just like hikers on Earth, the mission is looking to just go around and simply needs to decide if it's going to go around to the left or to the right as they move forward. The mission team has plotted out a two-phase path that lets Percy, once it gets around the danger region, sample a variety of environments around the former lakes, streams, and resulting deltas that shape Jezero Crater. And as they look at Nilium Planum beyond, they're figuring they're going to need a mission expansion. This is kind of normal. The current plan is they're going to pick up a series of rocks within Jezero Crater, leave that cache of rocks to be picked up by a future mission. Then they're going to exit Jezero Crater, leaving that cache behind and rove through Nili Planum, a volcanic deposit, where during a hoped-for extended mission, it will collect yet more rocks. As Ken Wilford presented, he talked about various features, including this feature, Kodiak, that could hold minerals and organic materials deposited by past life. He literally compared existing formations on Mars to similar looking structures on Earth created through the buildup of dead micro and macroorganisms and plant life. The path he and others are planning is a tour of an ancient habitable environment where they are looking for the chemistry of life. We've seen these comparisons before, but it never stops making me catch my breath. They're looking for the signs of life. Other speakers talked about this as a dried out aquifer, and questions arose about where best to look for these ancient life. And Wilford further commented that some believe the Martian subsurface is the best bet for life now, and also deep in the past. Yes, he said now. And yes, Perseverance was really well decontaminated, but all that said, Percy isn't going to go digging for life or go near places where life is likely. In Percy's images, the landscape so far looks varied with dust, bare-baked rock, mud-looking deposits, and a variety of other hard-to-explain minerals. My favorite of these are the holy rocks in the left side of the image behind me. These have been seen by other missions, but so far not by a mission that can rove up and sample them. These rocks look a lot like Texas holy rocks loved by aquarium owners. The similar looking rocks on Earth are made of limestone that has been shaped by water. I can only hope that Percy, with its arm and drill, will be able to reach out and finally tell us what these rocks really are. One final break, and we'll be back to bring you some of the non-Mars related science from LPSC. Stay tuned. Not all talks at LPSC are about Mars. Yesterday, the highlight of the meeting was exploration of all the places where oceans might exist beyond the Earth. And some of those oceans being discussed really made Earth feel like a desert dry world. Let's take a look at Pluto. Doctoral researcher Adine Denton presented a new analysis of New Horizons images that hint at Pluto having a 150-kilometer deep ocean beneath its icy crust. For comparison, the deepest point in Earth's ocean is the Challenger Deep in the Mariana Trench, which is just 11 kilometers deep. These results are thanks to a new analysis of Pluto's low-res side. During the New Horizons flyby, the mission got extremely good images of one side of Pluto and lower resolution images of Pluto's other side while the mission was further away. There are a lot of tricks to try and bring out detail in these images, and over time, as our software gets better, we're able to reprocess things and learn more. And in reprocessing the low-res side of Pluto, Adine and her collaborators found a fascinatingly located region with a fascinatingly disrupted-looking terrain. That location, exactly opposite from Sputnik Planum, the smooth heart-shaped crater imaged in such amazing detail. Many researchers have proposed that Sputnik Planum is actually an impact basin. If this is the case, when Pluto was hit by whatever it was hit by, the impact would have generated shock waves that traveled through and around the planet. On other worlds, we have seen a crater on one side and a disrupted terrain on the antipode, the opposite side, where the shock waves came together and tossed the land all around. Different kinds of land, planetary core, and stuff in between can all transport these waves in different ways. And to figure out what happened, Denton ran what she calls a small army of Pluto simulations that each had oceans of different thickness and cores of serpentine or other minerals that don't really matter because it turns out serpentine in an ocean of 150 kilometers thick produces the disruptions actually seen, we think, in the low-res images of Pluto. Understanding the interplay of water, rock, and heat was a recurring theme throughout this meeting. And when it comes to the interplay of heat and ice, melting is a common result. This comes into particular play with Neptune's moon Triton. Larger than Pluto, this captured KBO had to somehow drop a ton of kinetic energy as it went from orbiting the Sun to orbiting Neptune. While this can partially be explained if Triton, like Pluto, was in a binary system with another similar sized body, that doesn't explain everything. Triton would have started in a highly elliptical orbit going backwards around Neptune, which admittedly it's still doing. But that orbit would have had to become circularized and much smaller over time through tidal effects that changed the orbit while heating the world. In research presented by Noah Hammond, they find that this process would have taken billions of years, and depending on the composition of Triton, potentially could have completely melted this world's ice. In what was the sweetest analogy of the conference so far, researchers discussed how we can tell what is happening with better images of Triton by comparing how the ice melted on this world with how ice cream melts. Specifically, think of how ice cream melts and spreads when placed on hot pie. The top stays structured, but the entire surface spreads and the edges change. All it will take to figure out if this is what's going on is better images from a spacecraft. A mission named Trident is currently proposed, and if it is funded and makes it to Triton, its images of the meltiness of Triton will help us one day sort just what Triton is made of by looking at how it dissipated heat, like ice cream on pie. This has been the Daily Space. Join us again tomorrow for more from LPSC.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.